Thank you. I've got slides here somewhere. All right, as you know, I'm talking about telescopes. Actually, yeah, go back a slide so they can see the name. There you go.
Shall I start? Auto advance.
Go ahead. Yeah. So, telescopes, they gather light. They put it to where photo or your eye can see it. And, you know, the bigger the lenses are, the wider the lenses are, the more light they gather. This is really important. But it turns out when they get really big, they get really heavy. And since lenses that are the usual telescope shape are thin at the edge, it's really hard to hold up a lens like that. So mirrors, much better. You can support the mirror from the back of the mirror. One way to deal with some of these problems is to make a bunch of mirrors. Then you don't have as much weight to hold up. This is the Keck Observatory in Hawaii. But when I was in Tucson a couple of weeks ago, I found that there's a mirror factory under this stadium. So I thought I'd go check it out. And they give tours there, which is really excellent. One of the things that they had going on there was the giant Magellan telescope. I had been kind of vaguely aware of it, but I learned a ton about it, and that's what I'm going to tell you about tonight. This is the mold beginning to be fabricated for that telescope. The lens is actually, the mirror is actually going to be a set of 7 mirrors. This is a picture of what it'll look like on top of a mountain about 8,000 feet up in the Atacama Desert in Chile. And it's named after Magellan, who you've probably heard of. But it's actually named after the Magellanic Clouds, which are visible in the sky only in the southern hemisphere. Now, the other part of a reflecting telescope is at the top, there are some secondary mirrors, and this is, on the right there, was what they look like when you have actuators that reshape them with feedback so that the atmospheric disturbances happening can be corrected in real time. So it's a very sophisticated thing, and this really washed out. But down here in the bottom right corner, you can see chunks of glass, and they're spreading out the glass across the top of the mold. This is a 27-foot mold. It's 8.5 meters. The glass that they're using is special kind of silicate glass with boron added. It's made in Japan, and it's shipped over here, and they have to look at each piece and use a polarizing technique to test each piece. They throw away the pieces that aren't perfect, that have the wrong polarization. This is a huge clay vat. Every batch of glass has to be melted in these handmade clay vats using this Japanese technique. That's the only place in the world they make the right kind of glass, the telescopes, that don't shrink or expand. The glass has to not shrink or expand when it's exposed to temperature, and it has to be very stable glass. So, sorry, I was going to show you how they zoom it across the world from Florida. The sand gets melted in Japan, but the sand is from Florida. Then it comes to the US, and of course it's going to go to Chile for the telescope. So this, it's so washed out, it's hard to see. On the back here, there are a bunch of little holes, and you attach stuff to it so that when it's supported, it's very evenly supported, because when you have something that weighs tons, it's 18 tons, so you can see the holes here, it's so heavy that even a slight mismanagement of where the weight is distributed will break the glass. They also use those holes to blast out the mold, because the inside of the mold is hexagonal openings so that it won't be solid glass. It's like honeycomb in there. Now here they're polishing the surface, first with a diamond rough polish, and then they use a finer polishing instrument. And those polishing instruments also have actuators, just like the secondary mirrors, that are changing the shape of the pad so that the pad will exactly shape the surface of the glass to make the parabola. Here's a picture I took when I was there. The parabola on this one is nicely ground in, but this is a special lab because it's the only place in the world they can do this. They figured out how to not only make these hexagonal spacers inside so that there's airspace and it's not as heavy, but also they spin the whole thing while the glass is melted so that it forms a natural parabola, and they don't have to grind for 50 years, they only have to grind for 2 years to get the right shape into it. Now, while I was there, they were doing a side job because the bottleneck is the grinding, the polishing. So between polishing, while they can't polish 5 lenses at once. So they're actually doing another lens a mirror for another job in the meantime. This shows a comparison of sizes of all the different telescopes. Up in the upper left, those tiny ones are lenses, and these are all mirrors down here. The comparison, this is the one that they're building now, 7 lenses, 7 mirrors. They're actually making an 8th mirror to swap out when it needs to be resurfaced. So they were 5 mirrors into the 8 mirror process when I got there. And if you have questions, I'm here for you.
Not a question, but can you go back to the slide with the amazing pun about the Vatican telescope? I just think that needs to be appreciated.
I can't, but Michael can.
The one we're on?
No, 3 or 4 more back. Keep going, keep going, keep going, keep going. That one.
With the amazing what? Oh, the pun. You want the pun.
Just think you didn't have a chance to go over it. I think you need to be appreciated.
Okay, not a question, but nice, very nice, thank you. Yeah, this was one of the 2 mirrors made for the telescope near Tucson on Mount Graham for the Vatican. The Vatican and a few other organizations run the telescope at Mount Graham. And between the 2 different mirrors in the Mount Graham telescope, it's a very large apparatus. When you have 2 different mirrors, or 7 in the case of the giant Magellan telescope, you're just collecting a bunch more light and you're sending it to the same place for processing. But they don't have to be contiguous light rays. So for example, the 7 with the 6 around and the 1 in the middle, there are little gaps in it, right? Altogether, that thing is about 80 feet wide, effectively. It's actually 86 feet wide, but because of all the gaps, it's the equivalent of a circle that's 80 feet wide. So it just gathers light from more places. Jamie?
So they're grinding these things with a whole bunch of diamonds. That sounds expensive. How?
The diamonds are diamond waste. They're industrial diamonds. They're cheap. That's not the expensive part of the project.
I see.
Yeah, there's a lot more expensive parts of the project. And if you want a pile of diamond dust, you can go out and buy it. For 30 bucks, you can get a bag of diamond dust. Seriously, it's cheap. In fact, I was just reading, total aside here, I was just reading an amazing memoir from the early 1900s of a guy who was involved in the 1800s in a thing called the Great Diamond Hoax. It was in Wyoming. But everyone in the West was investing in this, and the way that they hoaxed it was they bought a bunch of these trash industrial diamonds for really cheap, and they stuck them in the ground and then brought investors there and like, look, there's diamonds. So yeah, you can get cheap diamonds if you want crappy ones. Yes?
So I'm still back at how the mirrors work. So the mirrors gather the light and focus them to one place.
Can you put it back to the second slide?
And that's better because you don't have to use the really narrow.
That one, yeah. So yeah, the light goes to what's called the focal point off of the mirror. You can see the rays being reflected from an infinitely distant thing that creates parallel lines.
So that's the front of the telescope. Right?
So this is the light coming in right here, and it's reflecting off the mirror right there, and coming to a focal point right here, where that's where the image can be created. Or it can hit a second set of mirrors that puts it through the hole in the middle. That's why there's actually a hole in the middle of the mirrors on many telescopes, so that you can get twice as much length. And you want twice as much length from most telescopes because it takes so long to grind a big curve like that. It takes really, really a long time to grind into glass of this high quality of glass, right? And so if you want to save years and years of grinding, you make the curve a little shallower, less grinding, and that way the focal point is going to be way out here somewhere, but you can handle that by having a secondary set of mirrors. With the giant Magellan telescope, they took care of it both ways. They made a hole in the middle with a secondary set of mirrors, and they shortened everything way down because they can do that using this amazing new technique of making a deep paraboloid in the surface of the mirror by spinning it when it's annealing, when it's cooling. Yes?
Can you, so you're talking about glasses, the old way of doing things, sort of an optical glass. Instead you use a mirror, but we're still talking about glass. When I think of a mirror, I think of the metal part. Can you talk about why we're still using glass
Yes.
in a mirror,
That's
which is not
good
very
point.
like glass?
Yeah, the lenses kind of telescope does need glass or something that's see-through. The reflective thing just has to have a surface on it. In fact, after they grind all that to a nice smooth paraboloid, they just coat it with a couple of molecules of aluminum, really thin layer of aluminum. And that's the reflecting surface. So why does it matter what's holding that reflecting surface up? Because this is going to be in a telescope that is being used at night in a desert on top of a mountain where the temperature fluctuates incredibly, and glass, in fact, borosilicate glass, in fact, O'Hara E6 borosilicate glass is the only known glass that when it's in a vast 27-foot wide disk won't shrink and warp under those temperature changes. That's another reason they have the holes in the back as well, is so that the honeycomb air gaps inside can take in outside air, and they can keep it air conditioned inside there so that when they open the thing up for the night air, it won't all suddenly be changing shape and temperature. It's a multi-method way of dealing with the temperature and shrinkage. Even the slightest bit of warping and shrinkage from the weight of it or from the wind or from the temperature or whatever can completely change the way that the images line up. And they actually have actuators on the secondary mirrors. The secondary mirrors are about this big. There's 7 of those as well. And they have 650 per mirror that instantaneously move around the shape of this glass, which is only about the thickness of a quarter, to adjust for the fact that the stars are twinkling. You know what twinkling is? Twinkling is just atmospheric disturbances. So when you have atmospheric disturbances, the computer instantaneously notices them and makes up for them by sending signals to the actuators to bend the secondary mirror just right to undo the warpage of the atmosphere. It's amazing. Huge computing power involved here. Yes?
So is this an advancement beyond like the sort of micro mirror approach? Like you said in some of the slides.
Yeah, can you go to the last slide?
Right, or more, maybe 100 smaller mirrors. It sounds like you're able to get the atmospheric distortion adjustment going on, even though it's a semi.
Yeah, on mirrors like the Keck
Yes,
Observatory,
exactly.
the actual primary mirrors, those 2 mirrors, are made up of a bunch of smaller hexagons which are connected to computers so that they can be co-phased, so that they'll all point in the same direction and all line up with each other, and so that the disturbances and whatever, gravity, everything that's affecting it doesn't ruin the image. Well, once you get larger than the Keck telescope, that's too much computing power. It's way, way difficult. So that's why they're doing it with the secondary mirrors, which are small, instead of the primary mirror, which they're just making these vast things that don't change. Did that answer your question?
Yes.
Okay.
So, yeah.
Any more question?
So there are 7 different mirrors, but there is still just one focal point?
Yes, 7 mirrors, 1 focal point. What that means is the center mirror, this one that has the hole in it that has actually the viewer is standing right there. That mirror is a normal paraboloid with very centered, you know, but the other mirrors are like saddle-shaped, the edges of a paraboloid. So together they make a giant paraboloid. So they all line up as if they're one big paraboloid. And a paraboloid, by the way, is the 3-dimensional version of a parabola, which happens to be a really nice nature-oriented shape, easy to get just by spinning the mold for 3 months while the glass is cooling.
But that works only for the center mirror then, for the central one?
No, because the difference between the center one and the side ones, though it's a very important optical difference, is only about a ½ inch of glass. And a ½ inch of glass can be ground in just a year or so. Yeah.
Thank you. Thank you, Walt.
And if you want a cheat sheet, you can take this that Sonia Viejba has in her hands, and she is going to pass along to the person next to her. And I didn't bring enough for everybody, but almost enough for everybody. So take one if you want. And the cheat sheet tells about other telescopes that are on this picture.
Thank you, Joel.
Thank you.
Yeah.
Hey.